In this video, we introduce Speedy-Splat, a technique to drastically increase the rendering speed of Gaussian splatting models. This is a joint work by Alex Hansen, Alan Tu, Gang Lin, Vasu Singla, Matthias Wicker, and Tom Goldstein, appearing at CVPR 2025. Gaussian splatting models 3D scenes with a large set of 3D Gaussians. Throughout this video, I will describe a single Gaussian in this model by GI. To represent ground truth poses, I'll use PGT, and for a specific pose, I'll use phi. For a ground truth image, I'll use IGT phi, and for a generated image, I'll use IG phi, where G denotes the set of all Gaussian parameters. Rendering happens by orthographically projecting Gaussians to the image plane. What this means is that all 3D Gaussians are transformed to 2D Gaussians with depths, where the depth is the distance between the camera and the Gaussian mean. After projecting, Gaussians are localized to tiles of pixels. The color of each pixel is determined by an alpha blending of the color of each Gaussian in that pixel's tile, ordered from front to back. The value of alpha is given by the 2D Gaussian value at the pixel times the Gaussian opacity. This rendering is differentiable, allowing us to optimize the Gaussian parameters via gradient descent. Optimization is done via a simple loss function, defined as the sum of an L1 loss and SSIM loss. Additionally, the scene is periodically densified by adding Gaussians in areas poorly reconstructed, and pruned by removing large and transparent Gaussians. Our insight in Speedy-Splat is that the rendering speed is primarily determined by two factors: the average number of Gaussians needed to render a pixel, and the total number of Gaussians in the scene. Let's start with the number of Gaussians per pixel. Here's a Gaussian projected onto the image plate. This Gaussian is localized by subdividing the image pixels into tiles. All tiles that overlap with it are stored in a map to be used for pixel rendering. However, Gaussian splatting is overly conservative when computing this overlap. It first computes a circle centered at the Gaussian mean with radius equal to the ceiling of 3 times the square root of the max eigenvalue of the Gaussian's 2D covariance matrix. Note, this extends past the actual Gaussian extent, and I'll explain why soon. Overlapping tiles are then taken to be the tiles that intersect the bounding square of this circle. And the final mapping of tiles include all the tiles that are depicted here. Our first speedup to this process makes use of a predefined threshold in the rendering process. Namely, the alpha blending ignores Gaussians with an alpha value less than 1/255. Using this threshold, we compute the actual elliptical boundary of the Gaussian extent. We can then compute the axis-aligned maximum and minima of this ellipse. These points then define a tight bounding box around the Gaussian. The tiles intersecting this box provide a much tighter localization for the Gaussian, and we call this process our snugbox algorithm. However, we found that we can further improve localization by identifying the maximum extent of the ellipse in each row or column of the snugbox tile extent. This can be done efficiently by considering only the global max and min points and the intersection points of the ellipse with the tile row or column boundary. I'll quickly walk through this algorithm. Starting from the bottom row, compute the points intersecting the ellipse along the line defining the top of this row, points A and B. The row extent is then updated from the minimum point x min to B. The next row, we compute points C and D. Carrying over A and B from the last iteration, this row extent is then updated to be between A and x max. Finally, for the top row, no points are computed, and the tile extent is updated to be between C and D. We call this our AccuTile algorithm. Empirically, Snugbox and AccuTile increase the rendering speeds by a surprisingly high amount. The numbers in this table are averaged over 13 scenes from 3 datasets. Interestingly, our algorithms also noticeably decrease change time. Next, I'll discuss efficiently reducing the total scene Gaussians. To do this, we identify a per Gaussian score, UI, that approximates the second-order impact of Gaussian I on the L2 reconstruction error. We then prune a fixed percent of Gaussians with the lowest scores. The second-order impact can be approximated by the outer product of gradients on each rendered image. And these gradients can be efficiently approximated with respect to the per pixel GI2D values. Note that for a projected Gaussian, the value of gi2d at pixel p is a scalar value, so the score becomes just the sum over the square gradients of the 2D Gaussian projection. The gradients of the score are already computed in the backward pass, so computing the score can be done in a single line of code. We update scene optimization to also periodically prune via our score. We found that we can prune a very high number of Gaussians during densification without affecting the reconstruction. We call this soft pruning and provide results when pruning at an 80% pruning ratio 3 times. After densification, we prune an additional 5 times at a lower pruning ratio of 30%. We call this hard pruning. Here we see the addition of pruning further accelerates the rendering speed. Notably, the number of Gaussians is also sizably reduced, as is the training time. For paper, code, and more video results, visit our website, speedy-splat.github.io. Thanks for watching.